Well, thanks for coming this afternoon. We're very privileged and honored to welcome Professor Silvio Micali from MIT. Last year, Professor Arvind, who's another very well-known professor at MIT, was visiting Bangalore, and so I harangued him quite literally, saying, can you introduce us to Professor Micali, and can we somehow get him to come to India and to Bangalore in particular? And we're very glad that he's finally here, and he's spending some time with us. Just sort of by way of sort of very brief background, Professor Micali teaches at MIT. I guess that's no surprise, given that it says MIT there. His advisor at Berkeley when he did his PhD was Manuel Blum, another Turing Award winner. Professor Micali's work has spanned, a variety of very important areas of computer science, from public key crypto systems to pseudo-random functions, digital signatures, secure multi-party computations, and finally to, of course, to zero-knowledge proofs, of which he's a co-inventor along with Shafi Goldwasser. And these days, more recently, he's been working on mechanism design. In fact, yesterday he gave a talk at IISc on mechanism design. And of course, in 1993, he was awarded the Gödel Prize, and in 2012, the Turing Award. So it's really a very special privilege and honor for us to welcome him and to hear him talk about proofs and the importance of proofs today.
Good evening, everyone. It's really a pleasure and a privilege to be here in Bangalore, and thank you very much for the warm welcome, not only to your city, to Infosys, but also to India. So thank you, Rohan, thank you, Narayama, Bhavna, and all of you that have actually helped me with Bhavna too. All right. So proofs, secrets, and computation. So today, what I want to talk about is something that we know and love, right? Proofs. At least in small dosages, they are good for you. That's what I'm going to claim. And actually, never mind that they're good, they can be even practical. So here is my first proof, and I suspect it's going to be the first example of a proof for many of you. So that is the first criterion of equality for triangle, right? That if two triangles have two sides and the angle in between equal, then they are all equal. I remember that when I was exposed for the first time, right, to this, I found it very puzzling. Why puzzling? Because, look at these other two angles or this other side that I never measured, I never seen, essentially. I sit on one corner, I look at my side and my angle, and I can deduce something about reality that is perhaps far away and not even a thing. I thought, how can that be? And the answer, I concluded, is that proofs can be very practical. And what is more practical than sitting here and deducing things over there? And I never changed my mind. So that's the mantra of today. Proofs are very practical. So what are proofs? Now, I'm saying to you guys, I'm sure that they have a more older tradition than we have, but in my side of the world, the proofs comes from by the side of ancient Greece. Here is my best rendition of it. And so since 2,500 years, we've been somehow distilling what the notion of a proof is until the work of Gödel and Turing. Here they are. The usual iconography shows them a little bit beaten up by the events of life, but I wanted to remember, as we all should be remembered, young, invincible, and undying. So they're very different guys. The one here on my right is Kurt Gödel. And he's German. Technically he's from Brno, now Czech Republic, but essentially German in education and type of thinking. He was the type of mathematician with incredible precision, extreme formality. He could dive on the other side of the ocean in search for proving his theorem, and he would re-emerge on the other side, clinching the proof on his teeth. Nobody was as amazing. On my left is a British gentleman, Alan Turing, who had a totally different approach. Turing had essentially a very intuitive way of proving things. And his approach was to simplify things until the proof essentially proved itself. And you say, what was so hard about it? It was really amazing. But even though they have very different approaches, these two gentlemen, to proofs, they agree on one thing. And that is, proofs are strings with very special syntactic properties. Here is one such string. You can put it down in a roll of paper, You invoke an axiom, you say if A is true and you just prove it and A implies B, then B is true, and you keep on going and going and going until if you succeed, according to these very strict rules, to write down the statement of your theorem, the theorem is true. All right, wonderful. 2,500 years of distillation, that's what we get. However, there is nowadays, not nowadays, but in the last 50 years at least, there has been a question of how efficient are proofs. There is no notion of efficiency in the Turing or Gödel and before Euclidean, if you want, a notion of a proof. Proofs are these type of strings with special property. It doesn't matter if they are too long. However, I claim that the moment in which verifying a proof is as time-consuming as finding the proofs, then something terrible happens. Then all mathematicians will be looking for jobs. And we don't want this to happen, do we? Or at least I don't want this to happen. So essentially I believe that the notion of a proof, unless we intrinsically bake in the very notion that the verifier should have an easy time in verifying a proof, then what are proofs good for, right? Otherwise you can just publish the statement of a theorem and then you say, colon, prove it yourself, if the time to find the proof is equivalent to the time or close off enough to the time of finding the proof. Good, so let's do that. Let's actually impose in the notion of a proof that somehow the verifier of a proof should have an easier time. How do we do that? We are going to bring two characters into the game. One is a prover, and the prover better be hardworking. In fact, we don't care as much as he works. We can just say, for all we care, he can take infinite time to find this proof. Right? That's a kind of a magician that is going to work there. But the verifier, that's us. We insist that the verifier be lazy, meaning that has a very simple computation to do. How lazy? Very lazy. In fact, I have to say it's a polynomial time lazy. Okay, so, and then the magician thinks maybe for 100 years, and then finds the proof and ships it over. That's a special string with this syntactic properties to the king, who actually somehow inspects it and accepts it. So, if this is the proof model, what should be an efficient proof? Well, elementary, Watson, as said in the 70s by Cook, Karp, and Levin, by the notion of MP, an efficient proof is a proof that A is short, so that you can ship it easily, and B is easy to verify, polynomial time to verify. Because if I give you a short proof, but then you have to think forever to check it if it is true, it's no wrong. You want short and easy to verify. And that's the notion of MP. Why NP? Non-deterministic polynomial time? Because theoreticians had to hire a PR firm to name what they do. And that's what you get when you don't hire them. So, let me give you an example of an efficient proof. Not me define it, except whatever I just said. I'm happy just to proceed with an example. Okay, here is our first theorem. We have two graphs, G and H. And the theorem is that these two graphs are isomorphic. What does this mean? In English, means that they are the same graphs, but they are drawn differently. Technically means that there is a one-to-one correspondence between the vertex of the first of G and the vertices of H that preserves the edges. So that if A, B is an edge in the first graph, then if the correspondence is pi, pi of A and pi of B are also an edge on the other graph, and vice versa. You may ask yourself, that's a theorem worth proving? I don't need any proof of that. That's very good, but let's assume that these are the two graphs now, right? 1 million vertices, 1 billion edges. Are they the same, yes or no? Oh, that is the type of thing in which you need a proof. But now to say, if you want to prove the stuff, how do you do it? You send somehow the correspondence, right? So you say, Marilyn may actually work a long time to find the correspondence, but say, dear king, here is the correspondence, the proof pi, 1 really is on the left, so 1 in G corresponds to 5 in H, 2 in G corresponds to 3 in H, and then the king checks that any time that there is an edge between I and J, there is an edge between pi of I and pi of J, and is happy with the proof. I claim this is an efficient proof. Why? Because writing down the correspondence, it doesn't take much longer, much more bits than describing the two graphs in the first place, and checking this is linear time. So wow, that is an efficient proof. Wonderful. So, and to say, well, efficient proofs are only for graph isomorphism. No, there exist efficient proofs for a variety of things, and I want to abstract that away and essentially think of it, efficient proofs correspond to the following. Assume you have an equation in many variables. Okay? And the question is, does the equation have a solution? Good question. Essentially, NP, the efficient proofs correspond to proving that there exists a solution. Why? Because it may take you a long time to find the correct setting of the variables, but once you do, you ship them over, the other side, the verifier, just plugs them in and verify if 0 comes out. Yes or no? Right? That is an efficient proof. However, let's ask a more harder question that we can solve. How about how do you prove that an equation has no solution? This is not so clear, right? Because you say, if there is a solution, you give them a setting of the variables. If you want to say there is no setting of the variables that makes the equation 0, oh, that's complicated, isn't it? It gets worse. How about if I want to prove the exact number of solutions in an equation, which in this case happens to be 2 to the 116 plus 17. I claim that A, you don't have enough time to ship them over, all these settings of variables. D, you don't have enough matter in the universe to write down this setting of the variables. D, I have not even enough time to read them, and never mind that, how do I know that you are not hiding somewhere another solution that you are not willing to divulge? Right? So these are very nutty problems. And then there is also some other harder question that I can raise that I'm going to skip for the sake of simplicity. Good. Now, what is the West point 2? The point 2 is to say, well, if there are things that we want to prove, like, you are a firm, you have an employee, and you say, find the solution to this equation. And the employee says, there is a solution. Unless you give him or her a way to prove it to you this, what are you going to do? So, what is the fault? The fault, I believe, is in the notion of proof that we've been using. So we don't want to live in a world, do we, in which we cannot prove that an equation has no solution, or we cannot prove how many solutions an equation has, etc., etc. So we have only one option, and it's to embrace a new notion of a proof. And that's what we're going to do. To do this, we have to think very hard, because if I change the notion of a proof, I can hide high aces in my sleeves and do strange tricks. So if we want to distill down the notion of a proof, out of all this boiling and reducing, what should come out? I think two things is enough to come out. That's what we care bottom line in any notion of a proof. A, I want to be able to prove all true statements, right? It would be a terrible notion of a proof. I can prove something, but not others. No, everything true it should be provable. At the same time, it better be that there is impossible to prove a false theorem. The first property is called completeness. The second property is called soundness. Good. And so here is another notion of a proof. We call it interactive proofs, and somehow we come up something in the 80. And I will be nice, given the warm hospitality, and skip the formality, but I'm going to tell you, in essence, what these proofs are. You remember, how do you learn proofs? I think you learn them like me in a classroom like that, right? With a teacher on the board doing things, and you ask questions, and you got it. But when we formalize it, for mysterious reasons, we formalize it like these syntactic strings. We think, what were we thinking? If proofs were this interactive process to begin with, why did we lose track of all this and formalize them as syntactic strings? Heaven knows. It's time to rectify history, and I want actually to redefine proofs as games. And let me tell you what this means. I means the following. Assume that there is a theorem, and I want to prove it to you the theorem is true. But it may take too long. It does not have an efficient proof. So what am I going to do? I'm going to prove to you how, classically, in old-fashioned way, by a string, syntactic string, that this theorem corresponds to a one game. In the following way, that this game, if the theorem is true, I have a strategy in which I can win all the time against you. On the other side, if the theorem is false, the corresponding game, no matter what I do, I can win at least half of the time. Okay? Assume that I've done this. I've proven this connection between the theorem that I want to prove true and the game. And assume, they say, well, you know what, Rohan, let's play. And let's assume that I play and I win. I play and I win. I play and I win. I play and I win 100 times in a row. Rohan, what are you going to think if the theorem is true or not? Probably true. Why? Because, you know, if otherwise, if I have at most a chance a half of winning, if the theorem is false, what is the chance that I toss a coin 100 times and I get head 100 times in a row, right? Very good. That is the idea. Well, that is a bit too general, right? So let's do it, look by an example. Okay? One example of this game. Which example? The simplest possible example, okay? I'm going to, it was much harder to figure out what the example was going to be than actually to use it. So it took longer to find the example, but I'm very proud of this example. Let's consider the following theorem. And the theorem is similar to before, but this time I'm going to tell you these two graphs are not the same. Which in some sense, look, is like proving that there exists no solution to an equation. Because I want to say there is no correspondence between the vertex of one graph and the vertex of the other graph that correspond the edges. Here you can see this by inspection, right? These two graphs are not isomorphic because the graph over there has a single cycle of length 4. The graph on the right has 4 cycles of length 4, right? The one around and the two in between. So it cannot be the same graph. Good. But again, we are looking at the very hairy graphs, right? Spaghetti type of things, and we need to be proven. Now, the Marilyn again, how the hell is going to prove it? When two graphs were isomorphic, it was enough to send the correspondence, right? That preserved the edges. But now, isn't clear what to do. You cannot certainly list all the possible correspondence. Even if there is just 1,000 vertices, there are 1,000 factorial possible renaming permutations of the vertices. So this is not going to work. So let's remember, at the end, ladies and gentlemen, only we want a proof in the smallest minimal sense. We want to be able to prove all true theorems, and we don't want to be able to prove false ones. Here is, let's focus on how to prove that the theorem is true. The king is going to lock himself up in a cage, Faraday cage, in the secrecy of his room. What he does, he flips a coin to decide one of the two graphs. Say, without loss of generality, he chooses G. Then he flips coins and takes a random renaming of the vertices. Okay, call it pi. Then, because he chose this renaming, actually he goes ahead and renames the vertices. Then he calls a graph C. And now he says, notice that this graph C, by construction, is isomorphic to G, right? We just did it. He ships C to Marilyn. And he says, Marilyn, prover, you told me that G is not isomorphic to H, right? I constructed the C isomorphic to one of them, right? You tell me which one. Trivialities for our magicians. We'll soon realize that, say, G is really a renaming of C. So he's going to say, sire, whatever you gave me is isomorphic to G. And the king say, that's good. Okay? Game is over. Okay? Marilyn won. He managed to convince the king. What an elementary interaction, right? The king finds out the C, the Marilyn tells him he's isomorphic to G, done. Now, I claim that Marilyn can win this game all the time. Why? Because if G is really different from H, no matter if we repeat it a second time or a third time, right, with independent coin tosses, no matter which graph the king selects, and no matter how he renames it, C is going to be isomorphic to exactly one of them. So Marilyn has a chance to exactly guess which graph the king has renamed. Okay? So we can prove all true theorems. If we play this game a second time, Marilyn will win again. If we play 3 times, we'll win 3 times in a row, etc., etc. Good. Let's now try to convince ourselves that Marilyn, however, no matter how powerful he is, he cannot convince the king of a false theorem. What does it mean, a false theorem? The theorem says G is isomorphic to H. The false theorem is that actually G is isomorphic to H. But Marilyn wants to prove the opposite. Can he? Well, if G is isomorphic to H, and the king proceeds as we just described, and sends C over, constructed by renaming at random G, what is true about C? That actually is isomorphic to both graphs, right? Because if C is the same as H, and C is the same as G, then is the same as H. Not only is isomorphic to both, but is a random graph isomorphic to both. Not a spatial graph, it's a random graph. So Marilyn, in order is a random independent graph select among all the graphs isomorphic to both G and H. So Marilyn has what should he say? How can he guess which graph the king has said? Okay? I claim that he has a probability of catching Marilyn is exactly a half. And I'm going to prove it by a metaphor. And that is the metaphor. You a guy and I now are going to play the following game. I'm going to give you, see this coin? Yes. It's a fair coin, at the tail, and I'm going to toss it. And if a head comes up, I'm going to say, Mamma mia, typical Italian sentence. If tails come up, I'm going to say, Mamma mia. Ready? Mamma mia. What coin do I have? What? Wrong or right. You have exactly chance a half to guess my coin toss. Why? Because the information, I gave you no information about the coin toss. Why? Because if head comes up, I tell you Mamma mia, and if tail comes up, I tell you Mamma mia. This is the same. The only difference is I have exponentially many ways to say Mamma mia. Because what I'm going to do, if the king chooses G at random, initially, as the picture indicates, what is the information about the coin toss G that he gives to Marilyn? It's a random graph isomorphic to both G and H. So it's a random graph whether he chooses a G or he chooses H. So, and of course Marilyn has at most a chance of a half. And so if you repeat it twice, the chance that you don't catch Marilyn is a fourth. And if you repeat it 300 times, in 1 in 2 to the 300. Why do I care about 1 in 2 to the 300? Because 2 to the 300s, my friends, the physicist tells me, exceeds the number of elementary particles in our universe. So if you are worried about events to happen that are smaller than 1 in the number of elementary particles in the universe, never mind any atom, never mind any protons and electrons, but photons or quarks, they invent them all the time, all of them, okay? They're less than 2 to the 300, right? If you're worried about events like this, I think you are in danger. You should go home and lock yourself because anything can happen to you, okay? Good. So essentially, QED, that is an interactive proof, right? But notice that we have no classical way, no short string, easy to verify. I don't know any way to prove classically and efficiently that two graphs are not the same. If you find one, I'll give you a PhD on the spot. And if you already have a PhD, I'll give you a second one, etc., okay? That's very, so, but this is an elementary interaction. What does this say? That if we change this notion of proof in this probabilistic interactive way, and we take such a problem that is so damn difficult, and we make it so elementary, what does this mean? That this proof system is very powerful. And you are right. And in fact, let's go back, if we define efficient proof like interactive proofs, now we change the definition. The old NP is just a special case of IP. How about proving that an equation has no solutions? You could do that too. How about proving the exact number of solutions of an equation? You can prove that too. And how about proving this, whatever P space is? You can prove that too. Okay? That is a very powerful thing. Wonderful. So what? Who is this guy? The skeptical guy who always says, what is this extravaganza, mathematicians, theoreticians? What the hell are they, like, why should I care? All right? All right, let's prove him wrong. Let's talk about cloud computing. When you hear the name cloud computing, you say, I heard about it, I don't know about it. Well, think twice. Because what we really have right now in our society is cloud storage, not cloud computing. Which means I'm afraid to lose my contacts, my thing, or I'm afraid that I have a computer meltdown. I upload to the cloud my stuff, and then when I want it back, hopefully I get it back. That is storage. Nobody's computing anything. But what is cloud computing instead? Is to say, Infosys, Google, Microsoft, right? Who you have much more power with my poor laptop, right? I cannot compute f of x, because that is a very long computation. How about if you do it for me? Sure thing. 6 months later, it says, Silvio, the answer is 27, and that's my bill, okay? And it says, $100,000, thank you for your trust. What trust? And he says, what do you mean, you don't trust me? Then you compute it yourself, and you can see that it's 27. Wait a minute, I went to you in the first place because I was unable to compute f of x. How the hell can I do? So you need, essentially, some form of this interactive proof so that you can outsource to the cloud computation that you cannot hope to do yourself, and you have a very fast, efficient verification, and you enable another business systems. Okay? Something which you don't really have right now. So, proofs can be very practical. Why? Because we used to think about oil being a commodity that people would kill for. They still do, but it's not the only commodity. Then we had gold, for which people killed for. People have always killed for land, because that's another scarce resource. But you know what the most precious resources in our modern world is? Is computation. So we have ways to trade and still sell oil, land, real estate, gold, what have you. But we don't quite have a good way to sell the most precious resource, which is computation, because we must have another very quick way to verify it. Otherwise, there is nothing to sell. Okay? So if we enable this proper selling of computation, we actually made it a better world, and the proofs can be very practical. Good. Now that the notion of a proof is a big one, right? Here is a snapshot. It's too big to fit in a slide. So if we start changing this, and we start tickling the sleeping giant, there is so much more that we can do with the world of proof. And I want to convince you of this. And my next topic is going to be zero-knowledge proofs. What does this mean? I want to answer the following question. How much knowledge is necessary to verify a proof? Certainly enough to convince you, right? But in general, it could be much more. Says, but how you can tackle this question? Here is, first of all, you have to ask a much bigger question. What is knowledge in the first place? Oh, really? Why to stop there? There is a better question, right? So it says, how are we going to do it? Then zero-knowledge proofs actually saves us, because he essentially is not a question to, I'm not going to define what knowledge is, but I'm going to define what knowledge is not. And I'm going to prove that a way to prove theorems in which I can reveal nothing but the truth of an assertion. Okay. And to say, well, I'm skeptical, and you should be, and therefore I'm going to tell you the rules beforehand. If you believe this, the Knowledge Act, which essentially is 2 axioms, if you believe it, I can convince you things ain't zero knowledge. The Knowledge Act consists of 2 axioms. The first axiom says efficient proof is for free. What does this really mean? Assume that you're taking a stroll in the city, and I meet you on the street holding an integer x in my left hand and an integer y in my right hand. And I'm saying, surprise, I have a great bargain for you, okay? You give me $1,000 and I'm going to sell you the product of x and y. Would you accept the bargain, the offer? I say, no. Why should I accept the offer? Why? Because multiplication is easy. So I can multiply x and y myself, and I can save $1,000. Okay. Unable to sell you the product of x and y, tomorrow I meet you again and say, hey, I have another great offer. You give me $1,000 and I'm going to sell you a 100-bit random string. Would you accept the offer? No, because I say, look, I have a coin the same way you do. I toss it 100 times and I get a 100 random bit string and I save $1,000. Thank you very much. Right? Good. So we are in agreement. We now believe in the Knowledge Act. That's all I need to do the theory of this knowledge proof. Essentially, probabilistic, efficient computation is like the air we breathe. We don't pay for it because it's available to everybody. Good. Let's go back now to the theorem. Remember where 2 graphs are the same. And the classical proof is I ship the correspondence. This classical proof, we were lucky because for isomorphism, unlike not isomorphism, the classical proof is efficient, is short, and easy to verify. However, he gives too much knowledge. Well, I don't need to define knowledge to convince you of that, right? I have one question. Is G isomorphic to H? Yes or no? I have one bit question, right? But when I prove it, I actually give you the entire explanation. I give you the correspondence that was very hard to find, from which you can deduce that the two graphs are not the same, and so much more. Okay, so let me give you an alternative proof. Ready? Here are two graphs, G and H. Marilyn claims they are isomorphic, but that does not want to reveal the correspondence, and worse, nothing else. He doesn't want to know, reveal the number of correspondence, or there is a correspondence in which one corresponds to an even number on the other side. Nothing at all, okay? How does he do it? He flips coins to come up with a third graph, C, isomorphic to both G and H. Okay, he can do that, right? Then the king tosses coins, and you say, you, Marilyn, told me that C is a random graph isomorphic to G and H. Choose a random between G and H, chooses G in this example, and you say, prove to me that C is isomorphic to G. Marilyn says, okay, here is a correspondence. Notice that there may be 1, 2, 3, 4, 5, who knows how many correspondences that preserve the edges, isomorphisms between G and C. Marilyn takes a random one and ships it over, call it phi. Now the king says, okay, because once you have a correspondence, you check it, as we did before, and you realize C is the same as G. The end. He accepts it. Now I claim that all true statements are provable this way. So if G is isomorphic to H, Marilyn wins this game all the time. Because I don't care which graph C Marilyn chooses. No matter whether the king chooses G or H, Marilyn will find the correspondence with C and G, and it will give it to it. Check. How about proving that false theorems don't get proven? Well, if the theorem is false, what does this mean? That G is not the same as H. Then I claim that no matter how cleverly Marilyn chooses the graph C, with at least a probability of half, right, the king is going to find Marilyn the fault. Because if C is isomorphic to G, it cannot be also isomorphic to H, if G and H are different. And if the king says, prove it to me that C and H are isomorphic, he cannot do that. And this has a chance at least a half, right? So by magic, this is an alternative proof, interactive type of probabilistic proof as we saw before. Okay, but that seems to be more complicated than sending the correspondence. Yes, but this has an additional property. This way of proving things that I just said, it conveys nothing but the truthfulness of the assertion. Says, how do I know? This isn't clear to me, right? Because after all, I have a magician on my service. He proposes me a graph C. I can choose the magician to say, prove it C is isomorphic to G, or prove it to C is isomorphic to H, at my will. How do I know that I cannot extract some information about G and H in this fashion? Excellent. How are we going to do it? Essentially, I want to say, listen, I want to prove that this way of proving things conveys the truth, which it should be, so you can squeeze the stuff, you can squeeze that C, G, and H are isomorphic. But that is the purpose of the proof. But nothing else. How do I know? How do I say that? I say it this way. Because if I knew beforehand that G was isomorphic to H, then the proof doesn't tell me anything anymore. Why? Because I can reconstruct the proof with exactly the same odds in which the prover and I would have constructed together. It's clear enough? You give me something, this something I extract that the theorem is true, but nothing else. Why? Because if I knew the theorem is true, I can simulate you, I can generate by myself, efficiently, a proof in the same way which you and I could generate it. And therefore, if whatever I can do efficiently is for free, there is nothing in this proof. Can I really generate it? Well, let's assume, let's put on the side the Marilyn. And let's say that now we have only the king. Remember, the king is polynomial time. The poor guy can only flip coins and do easy computation. Here is the easy computation I'm asking to do. in his mind, right? It's a flip a coin and choose a random between G and H. Say, okay, I choose G. Flip a coin to find a random renaming permutation of the vertices. He chooses phi. Rename G according to the permutation you just did. Okay, I get C. Then, write down C above an arrow from right to left. Done. Write down G above an arrow from left to right. Done. Write down phi above an arrow from right to left. Done. Okay? If the king knew that G was isomorphic to H, he could generate this triple. How does this triple compare with the proof that G is isomorphic to H given by Marilyn? Let's have a look. Is a triple and is a triple. So what is the first entry in this triple? I claim that in both cases, the first entry is a graph at random selected in the class of graphs isomorphic to both G and H. So there is no difference in the first entry. What is the second entry? In both cases, the second entry is the coin toss. The coin toss is done in different orders, but it's still a coin toss. And what is phi? Oh, phi is a random permutation between G and H. Right? In both cases. So in other words, the distribution of this triple is the same when the king is isolated at home or where he talks to the prover. And because whatever the king can do over here is extremely easy and is free and it is deprived of knowledge because it comes for free, whatever he can do by himself has no additional knowledge. But that essentially proves that this way of proving things proves that G is isomorphic to H, but nothing else. Okay? If you really want to prove it, the protocol is true. That is the essence of the proof. There is a little bit more to prove. Okay? But that is always the case. There are technicalities that one has to address. But it is actually, the essence of the proof is really this argument. I really want to tell you that this stuff should remind you of something that you went through your life, hopefully in your younger age. I went through this phase. I'm sure you did too. So what is this phase? The phase is that at some point in life you become sophisticated enough that you realize, does the world exist or is it a fruit of my imagination? Right? I mean, does that sound familiar? I mean, it does, right? So in fact, for me, even I went through this phase was a bit too long, right? Because my mother, I remember, started getting worried and says, Silvio, I think it's time to go to school because the world do exist, right? And in fact, I do exist, and I tell you that you have to go to school. She says, Ma'am, there is no school, there is no you. I'm thinking that you are just telling me these things. No. So you cannot break the symmetry, right? So that is the thing. So that is essentially the way in which we are reappropriating this very basic young emotions as human beings and transforming it into a scientific statement, which is about the knowledge of doing a proof. Very good. By the way, I just proved that a particular theorem, graph non-isomorphism, has a zero-knowledge proof. Do zero-knowledge proofs exist for only that theorem? For a few theorems? For some special theorems? Ladies and gentlemen, no. It is actually a classical theorem that everything provable is provable in zero knowledge. About the Fermat's theorem, that too. Okay? Nothing, doesn't matter. Anything you can prove, that is an intrinsic property of proofs. So what? It's okay. I thought, so what is this business of hiding knowledge of a thing? Is another extravaganza deprived of any application. Oh, really? Let's try to look at something that we consider practical. What is more practical than a password, right? Everybody of us has passwords. And passwords have been in existence since prehistoric time, I believe. But I'm going to, given that the hour is short, I'm going to shorten it. I'm going to put in some medieval time. So there is a valiant knight on one side and a gatekeeper of a castle on the other. And the knight can get in if and only if he knows the right password, which in this case happens to be Open Sesame, and he gets in. By the way, that's essentially the password, right? Essentially. There is one problem in medieval time and in modern time, that if in medieval time there is an enemy in the moat around the castle, under the water, hiding, and hears the password, tomorrow he utters the same password and he gets in too. Right? It's a major problem. Is this the only problem of password? No, there is worse. Why? Because if you are not different than me, I forget my password. So I memorize 10. After that, I have no storage for password. So what I do, that I duplicate password. I use the same password to authenticate, say, myself to MIT and read my email, or to get money from my ATM machine in a Bank of America. So the problem with password is that the second problem is that the gatekeeper ought to know the password, because otherwise, when I say open sesame, unless he knows the password is open sesame, so he ought to know. And once he knows, sooner or later, the gatekeeper has a brilliant idea. He goes to Bank of America and says, good morning, open sesame. I'd like to withdraw, $1 million, okay? That is a problem. But now, how can we solve this problem? We solve it this way, by zero-knowledge proofs, as follows. I'm going to tell MIT, I'm going to tell the castle, I'm going to tell Bank of America the statement of a theorem that I generated and whose proof only I know. A particular statement, by the way, which is very compressed and easy to do, you take 2 primes at random, that is easy to do, and you can multiply, which is also easy to do. You get a product. What is special about this product? That nobody has any idea on earth how to, given the product, reconstruct the 2 primes. So I'm going to tell MIT, listen, anybody who proves that this n is my n, anybody who proves to you that this product 2 primes, let him mess around with my files. Okay, give him access to any file that I have, because that is me. And I'm going to go to Bank of America and say, if somebody proves to you that n is product 2 primes, this n that I'm giving you now, let him wire money abroad, let him do whatever he wants, because it's me. Okay. But when I'm going to prove this, I'm going to prove in zero knowledge. And if you remember what the magic property of zero knowledge is, that this proof, you can extract only what? That the statement is true. So the verifier, say MIT, I identify myself to MIT, I prove it, n is product 2 primes. What does MIT know at the end of the proof? N is product 2 primes. Big deal. Can now prove this to somebody else? No, because if you have only the mere statement of a theorem, by definition, you should not be able to prove it. And therefore, it's safe to use the same password everywhere. And hearing the proof is not going to help, because not even the verifier of the proof cannot impersonate you. Certainly not even somebody who listened in between. So, ladies and gentlemen, we have here a password system which has perfect secrecy, provable non-impersonality, and even satisfy the third property that I have not the time to describe, which is total deniability. So, once more, if passwords are practical, proofs are very practical. By the way, I want to say that this business of zero knowledge extends not only for proofs, but actually to secure protocols. And what is a secure protocol? It's an interaction between essentially 2 people, one on top of a safe, and inside the safe there is his or her secret key, SK. And then there is somebody else who does not have the secret key. And what does the protocol do? Oh, they do a bunch of stuff, very complicated protocol for we have protocols, cryptographers for everything. But the point is that if I never use my secret key, theorem, the secret key is safe. Well, it better be, because I'm not using it. But if I use it, what does this mean? That I must send at some point in the protocol a message that has to depend on my secret key. What does it mean? It is a function of the secret key and something else. Now, the moment in which I take this message, that is a function of the secret key, essentially this message ought to, the danger is that like a distorted shadow on the wall, you cannot see the secret key exactly, but because it depends on it, you get some idea about the secret key. And if I send a second or third message, you put all these shadows together and you reconstruct maybe my secret key. But the solution is to minimize knowledge loss, because if I can use zero knowledge in such a way I can prove that no knowledge is leaked from these protocols, I have a really true secure protocol. And that is something very, very hard to do, because when something does not work, very often we can at least detect it. Right? If my faucet of the hot water is broken, no hot water flows. And if I call the plumber to fix it and say, oh, now I open it, there is hot water, most probably the faucet works. Right? But you never know if a cryptographic system works, because whoever is really has the interest of realizing that it's not working is not going to tell you. You think, oh, your system is great, it's so convenient to use, my wife uses it too, I love it, okay, but unknown to you is leaking everywhere and you don't even know. So, zero knowledge is actually crucial for cryptographic protocols. But I don't want to go into this direction. Remember, I wanted to sell you proofs. So let me tell you whatever has happened, additional things, very briefly, among proofs. One thing is the sampleable proofs. By the way, one of the major things, as you know, A over here is Aurora and S is Sudan, so they had a very big saying into sampleable proofs. These were things which are not even in our radar screens before. So these are proofs. You remember that proofs ought to be that you read every single bit of them, right? Because if you bypass, if I know that you don't read the middle of a proof, I assume it's 0 equal to 1, and I can prove anything ever since. So these are sampleable proofs means that there are proofs that you encode them in a special way, which they become longer, but after become longer, to check if the proof is right, I can somehow sample it. Even if I'm sampling 3 bits, I can deduce a probability half whether the proof is right or wrong. Magical. Here is another thing, CS proof, computationally sound proof. What does this mean? These are proof systems which are both complete and inconsistent. What does that mean? Well, these proof systems are so good that you can prove both X and non-X all the time. Says, gee, this is not good at all, right? What do I care about being a very efficient proving X and very efficient proving non-X? Yeah, but there is a caveat. Even though every statement, including false ones, have a good-looking, short and easy-to-verify proof, it is a theorem that to find this short but not too short, easy-to-verify statement is extremely hard for false statements. So assume that I want to tell you this number is product of 2 primes. And I convince you, I give you a very short proof of that. Or I want to prove it to you that whatever assertion. And then you want to know, well, either the theorem is true or Silvio's worked 2 to the 100 years to find this. Which is of the case do you believe it to happen? Well, that the theorem is true. Why? Because I don't have 2 to 100 years. Right? And in fact, nobody has. So in a sense, this is a safe way to join 2 opposites, life and death, Eros and Thanatos. And you know that when you put 2 opposites together, you reconcile them somehow. That's where power is. For instance, in every religion, in every mythology, who is the most powerful god or goddess? Whatever is the god of 2 opposites. Look at Shiva, the creator, and Shiva, the destroyer. He is the most powerful god, and that works for everybody. So here, what we are doing, we are essentially putting completeness and inconsistency, which are at their opposite ends, and reconcile them in a logical, usable way. And what do we get? Why do we disturb the gods for doing this? Because now we have a proof system in which not only is easy to verify, but it's also easy to prove. Because what I did not notice before is that to prove things efficiently for the verifier, the time of the prover had to become much, much, much bigger. So much so that it was hard to find such proofs. Here instead in CS proof system, the time of the prover goes millimetrically up and the time of the verifier goes very down. And that is, I believe, a good healthy balance. Rational proofs, what are these? These are truth for money. Okay? I want to know f of x and I go to you and I give you a contract. Easy to evaluate contract. And the deal is, no matter what answer for f of x you give you, I pay you money. So, gee, that's my lucky day. If I tell you the answer is 27, you pay money? Yes, I do. If I tell you it's 33, you pay money? Yes, I do. No matter what I say, I pay money? Yes. So, but there is a caveat in which the payment rule, which is very simple to evaluate, is such that you maximize your money if and only if you give me the true value for f of x. That's another way to do so. And that is another approach to truth as the maximization of easy to compute function that we didn't know about it. And finally, to close it, there are snarks, P affirm not being there, of course, succinct and interactive arguments on knowledge. So these are actually my students that are very lucky to have great students who flushed out all this. And let me tell you what at the end is. These are proofs, in fact, zero knowledge proofs that are so simple, so compact rather, that you can barcode it and use your telephone to scan the proof and verify whether the theorem is correct or not. Right? That's very much. So you can actually have proofs and zero knowledge proof anytime, anywhere. So, wrapping it up, classical proofs have been living with us for thousands and thousands of years, the classical notion. But then suddenly, in the last 25 years, there was an acceleration. MP, IP, PCP, CS proofs, snarks, rational proofs, in a space of a single generation. I want to say that is really amazing, because I've seen in the construction we have erected to the skies beautiful structures. Here is just one, just because I'm Italian. But it took us generation over generation to build these things. The notion of a proof is no less beautiful than such cathedrals, than such buildings. But we have a big difference. In one generation, we're done. That is absolutely amazing. I cannot tell you how fortunate I feel to have been part of this generation. So, in closing, I want to say that proofs, love, and war have something in common. And what is it? Everything is fair in proofs, love, and war. And why is it? Because we care. Right? We care so much that we go to excesses when we care so much. And in fact, look at what we did with the poor notion of a proof. It used to be syntactic, now it became an interactive process. It used to be strings, now it's an interactive process. It used to be right with probability 1, and now they are right with probability 999999999. So they used to be that you had to read them all, now you can sample to read them. We had done, to use an Italian expression, mincemeat of this notion. We had dissected in all possible ways because we care. So, and when proofs, love, and war are also the same, because these are the type of activity in which you have to engage, not with, as a side job, but with your whole being. With your brain, of course, but also with your emotions. They pop up in defining these things, your personal history, and finally, your personal sense of aesthetics. So proofs, I claim, are quintessentially humans. It used to be that language was quintessentially humans. Now we know that cats and dogs talk too, different language, but somehow cats have never proven a theorem, as far as I know, and so that is our last human thing. We cling to this piece of humanity there. And the proofs are really magical because they still are this bridge between rationality, what is true inside, and what is true outside, that somehow converges miraculously. And I claim that they are going to be more useful as complexity goes. Ladies and gentlemen, the world, you know, is getting more and more complex. And our survival as a species is going to depend on some great piece of machinery, more and more complicated, which has to work, otherwise we perish and die. And the way it works is going to be proofs that actually the only thing that can actually able to handle such complexity. So future are our past, our present, and I believe they're going to be our future. And that, I believe, ends the scientific part of all this. And now if there are students, I want to have some piece of advice. Because the truth is, I always love to give advice, but now I feel a little bit more legitimized to give it, okay? So here is my 5 minutes of advice for the students that I see, at least there are a few of them there. And the first piece of advice is embrace computer science. Look, I don't care which field that you're in. Whatever field you're in is good, but take courses in computer science, because that is a wonderful field. And he's going to hold the key, he's going to give a great contribution to our understanding mathematics, biology, economics, quantum mechanics, you name it. So really computer science is like the invention of fire has revolutionized the world we live in. So the great charge of balaclava admittedly was a very low-tech affair, right? However, it is perhaps the best way to convey the impetus and even intellectual ferocity of our community that, totally fearlessly is taking, bigger and bigger problem. So do take computer science, join us in this adventure. The other thing is collaboration. These are my graduate fellow students at Berkeley, in which I'm proud to have proven several theorems with Michael Sipser, Vijay Vazirani, and David Lichtenstein. And why? Because science and research is not a zero-sum game, and collaboration wins over competition anytime. And don't take it from me, it's simply true, is much more fun too, okay? The second advice, confidence and doubt. I really believe that without confidence, nothing worth achieving is ever achieved. But doubt is important too. Why? Because if you, as a researcher, lunge in a direction, knowing beforehand that you're going to be successful, ladies and gentlemen, you're not pushing yourself hard enough. Okay? You have to push yourself to the point in which you start doubting you're going to get alive from the other side. The other advice is fortune. Never be ashamed of luck. And my ancestors, the Romans, define luck, that without which nothing. And they were right, and they believed it so much that they erected a big mountain transformed into a temple, the temple of primeval fortune, which is really a sight to see. And fortune exists in science and research too. And fortune has many forms. One is timing, to work on the right theorem with the right collaborator at the right time. Another good form of fortune is ignorance. Because if you see very well the enemy you are going to fight, you're going to run the other way rather than attacking. So not to have the sense of what you are up against is a really good sign of luck. Another good sign of luck is myopia. Because again, myopia is very important because you belittle, you don't really think that it is so going to be so difficult, and that is a great stroke of luck. So my advice to you is be lucky. Stubbornness. I'm as stubborn as a mule, and I am proud of it. Because stubbornness really means believing in yourself when nobody else believes in you. And for instance, this zero knowledge proofs, when we first came up with Shafi, we felt so proud and said, this is going to be a big hit. We are going to get published in Fox and Stock, the voice for you, not in the know, are really prime conferences in theoretical computer science. Wow. They got canned right away. But unabashed, they say, well, they must have made a mistake, so let's republish it. We were smart because we changed the title, so to mislead the committee, right? So this is not the same thing. Well, canned. Okay, so then we had another revision, the information content of a Prof system, and says this time is going to make it. But finally, we got the thing. So we acquired a third order. It says, Shafi, Silvio, let me tell you, you don't know how to write. Do you mind if I do? And he actually finally produced the introduction that actually reads well. Here it is. Communication is a tool for transferring or exchanging knowledge. In traditional computational complexity or communication complexity, the goal is to communicate as much knowledge as possible, as efficiently as possible. Since all participants are considered good friends, no one cares if more knowledge than necessary is communicated. The situation with respect to cryptographic protocols is very different. What a beautiful prose. No. Finally, somewhere, somehow, I don't know, we found the right committee, okay? So my advice is be stubborn, believe in yourself. Another thing is limitation, right? So as a young person says, I want to do good, but I'm so limited. How the hell am I good? So turns out that the limitations are actually our strength. So much so that it's actually a time-honored technique to limit yourself to strengthen yourself. And no better example is the one of Hernan Cortez, who in 1915 disembarks in Mexico with a few hundred men against an empire, and the first thing he realizing that he's in a weak position, he decides to make stronger. How? By sinking his own ships up to an rival, and thereby giving an impetus to victory that really led him to win himself an empire. So enjoy your limitation. Other thing is that inspiration says, but I've been actually asked yesterday by a very smart student who really asked the question, says, how do I find the right direction, right? So where should I look? And there is actually a wonderful Russian writer, no less than Lev Tolstoy, who actually gives us this piece of advice. If you want to be universal, speak of your own village. And that is very true. And actually claim is not enough. You can actually go smaller. If you think about the upper left corner of your left ventricular system is good enough. Here it is, right? Because if you really speak about what matters to you, really somehow that is because the commonality of us human beings is such that your chances of being universal is extremely high. So my motivation was, as I hinted all of a sudden, is there someone out there to interact with? And if there is, should I fear the interaction? So what is yours is up to you to find. The path of self-discovery is a tortuous one, very convoluted. But I found my guardian angels on the way, and I believe you will find yours. So I know that our path is so long and our legs is so short, and that is very true. But at the very end, let's be frank with one another. Do we have anything better to do than trying to figure out who we really are and what do we want in this life? I don't think so. So let's accept our destiny, let's pack our belonging, and let's start our journey step by step with confidence, with doubt, with joy, and most of all with good luck. Thank you.
I saw in your statements there proving completeness and you talked about lack of integrity.
Consistency. Consistency and completeness.
Yes, consistency.
Yes.
I obviously didn't understand it because Kurt Gödel has proved that every formal system has statements that can't be proved right or wrong.
Exactly.
I just want you to kindly explain that.
Yes. Thank you very much, Mr. Murthy. So indeed, Kurt Gödel is famous theorem. In fact, the real reason for which he wanted to formalize the notion of a proof was to actually to prove the theorem that any sufficiently rich mathematical system, you had to pick and choose. Either is complete, so that any system in the theory, any theorem in the system can be proven, or is inconsistent, so you can prove A and non-A. But you cannot have both, right? So you have to choose. You want a complete system, but you never know if there is some inconsistency, or you have a consistent system, but you have to accept that there are theorems that you cannot prove. And he says you have to choose. And what I'm saying is that you can have your pie and eat it too. Of course, this way means that, however, means that you have a system which is complete and inconsistent. But that is a contradiction, yes. But Kurt Gödel, no matter how great he was, he forgot something, and complexity. And so, what if I have a system in which there are proofs out there for every possible theorems, but the proofs for the true theorems are in some sense nearby and I can pick them. And the other one for the false theorems are so far away I can never reach them. Essentially because with complexity means these proofs are sufficiently short, but if they are shorter than 300 bits, I cannot even guess them, right? But I can construct these 300 good-looking bits for the theorems that are true, and for the theorems that are false, there are these 300 good-looking bits, but the time to find them is going to be astronomically high. So I think that even de facto will never run in our lifetime or in the lifetime of our universe into a contradiction, because we'll have simply no time to find a good-looking, this magic good-looking figure. We only know how to do it for the theorems which are true. So in essence, this complexity allows us to have our cake and eat it too, and allows us to make sense of a system which is both complete and inconsistent. And by the way, I really believe that part of, first of all, complexity was not around at the time of Gödel, but there are also many other social aspects that may have prevented him to get there. And what are they? Now, our world is fortunately getting better, and our living standards are growing and keep on growing, and I hope that everybody is going to be having a nice life. But our life, however, is becoming more precarious and dangerous, right? So there is some probability, epsilon, non-trivial, that we annihilate each other off in one way or another, right? The nuclear weapons or whatever. And once we live enough time in which, these incredible weapons or these things that can actually destroy all humanity, it's much easier to accept the possibility that a proof can be wrong with some small probability. Because these are really concepts of our time, that in ancient time, I want to say, I may be poor, I may be thin, but the world is going to go forever, and humanity has a very bright future for a long, long time. So I believe that we are now primed for accepting a little bit more rigorous, but a bit more flexible notion of a proof.
I have two questions, but maybe others have questions. So I'll ask one, and then if nobody
Okay.
asks, then I'll ask the second. Slightly more, since you've talked about proofs in sort of great detail, and I've been reading Thomas Kuhn, and I wonder, what is your view on Are proofs, for example, are interactive proofs or zero knowledge proofs or any of these proofs, do they exist in nature or are they invented?
Do they exist, sorry?
Do you believe proofs are discovered or do you believe proofs are invented? With a slight distinction between something that exists in nature and something that you create.
If you are asking me, I'm going to give you my subjective version. And I'm not sure you're going to like it, but it's true to me. And that is, there is no difference. I really believe that whatever our mind and the universe and God coincide. I mean, there is really no difference. And in some sense, all the notion of zero-knowledge proof is really about this impossibility of breaking things. So I really believe that collectively, we are the universe. And so whether the universe exists without us or without us, I'm not sure. For me, it is not, to me, mind and the universe are one. And that's why perhaps magical, perhaps mythological, but that's why it's my own personal explanation of why this magical connection between proofs and reality exists. Because at the end, we are one and the same, I think.
One of the kind of emerging threats to classical crypto is this whole quantum computing emergence, right? How do you see that play out in your notion of very complex thing to prove inconsistency? Like, how does that break out? Suppose you have quantum computing tomorrow.
Right. So I believe that whatever I said is largely independent of the computational model, in the sense that, first of all, we must define what is efficient. And now, before quantum computers, I'd say with Turing machines, is a polynomial time Turing machine, right? Now to say, well, now we have quantum computation. Well, we have quantum polynomial time. So that would be, so in some sense, I think we just we should elevate and do that. And I'm agnostic about whether quantum computing really is a reality or not, but I believe that, it should be possible to bringing into the picture without disrupting much things. At least for the things that I discussed today, this is not going to be affecting. If you ask me about whether factoring is hard, then I should change my example, because factoring with a quantum computer. But in terms of proof theory and things like this, it should not be much of a difference. I agree with Mr. Murthy, but I'm saying, but I can see the point, right? So what I said, what is for free? What is deprived of knowledge? Tossing coins, I said, and polynomial time computation. Now to say, what is, if quantum computing becomes available, what is deprived of knowledge? Tossing coins and quantum polynomial time computation. But I think, the theory will survive this, because essentially it's pretty much intrinsic. Right? The notion of simulating somebody else means simulating in what time, in whatever efficient time. And so if you redefine efficiency, you should be able to lift this theory. I think that actually, one of the greatest frustrations as a theorist is the slow time of adoption. I mean, I thought that there will be, it says, oh, thank you, you want where is you're missing your zero-knowledge proof, here is one, take mine, you give it tomorrow. So somehow it has been, however, passwords are actually been used in password system. This much has been used. The full-fledged power of secure protocols mysteriously remains untapped. And in fact, I believe that, the first one who is going to actually deploy it, and deploy it for real, is going to really rule the world. I'm saying right now there are many more exchanges in the world. Right, it used to be New York Stock Exchange was ruling, but before London, now New York, and so unfortunately now we have many more. But the services they offer are kind of limited in all the world. And with all these secure computation, we can have very strange financial transactions that you could do that have no parallel in the world, and yet would be very nice to have. And so the first one who does this and really does a full-fledged offering to the consumer is going to hit it big. But but I've been predicting that they're going to adopt it in the next year, and I have to come to terms that maybe not in my lifetime. What can I say?